Fine. Right, ladies and gentlemen, good afternoon. We are going to start with chapter 4. We are making use of the textbook of Cengel and Ghajar, and chapter 4 is on transient heat conduction. You've already completed chapters 1 to 3 in the textbook of Cengel, in which you've looked at conduction heat transfer, and what was very important is that conduction heat transfer had lots of similarities with electrical circuits in terms of resistances, and the conduction heat transfer in all cases could have been written as one or other resistance component. So a continuation on that is now chapter 4, transient heat conduction, and let's immediately start with the title. What does transient really mean? If we look at a body, and that is in an XYZ coordinate system, XYZ, and here's the body, and we are interested in the temperatures of this body at different positions inside it and maybe even on the surface. If we have steady state heat transfer, steady state, and we would look at all the temperatures, then the temperature as a function of time, and that is the very important thing here, then the temperature at point 1 will stay constant as a function of time, as well as the temperature at point 2, temperature at point 3, and maybe there's the temperature at point 4. So there are no changes as a function of time. However, if it is transient, then the temperatures as a function of time would change. So that might be the temperature at point 1, that might be the temperature at point 2, the temperature at point 3, etc. So transient means it is dependent on time, and therefore we would like to get the temperatures as a function of time. The first paragraph is called lumped system analysis. A lumped system analysis. What does lump mean? It means it behaves the same, and it would mean that if we look at different bodies, as I've showed you here, which is not a lumped system, then the temperatures as a function of time will do something like that, 1, 2, 3. While for a lumped system, the temperature at point 1 will have that behavior, the temperature at point 2 the same, the temperature at point 3 the same, etc. So what does it mean? It means in a lumped system, we can determine the temperature as a function of time, but it would be bodies in which the temperature distribution inside the body is the same. There's no differentiation as a function of temperature. Examples. What are good examples? Good examples is a small copper ball. Small copper ball. If this is the small copper ball, okay, and you would put it on a fire, and let's suppose the fire is at 110 degrees Celsius, then very quickly the temperature distribution inside this copper ball will be 110 degrees Celsius everywhere. There's no temperature changes inside the body. However, if you take a nice thick steak, okay, and you're having a barbecue, and you've got this big piece of steak of yours. Okay, and I'm going to enlarge that. So if that is now the thickness of the steak, okay, then the temperature on the surface might be 110. Okay, but there the temperature would be 90 degrees Celsius, there it would be 90, there it would be 40 degrees Celsius, etc. So you can see what I mean. There's differences in the temperature inside the body, while in this case, the lump system, there's no differentiation in terms of temperature. Now, in paragraph 4.1 specifically addresses the lump system approach, and paragraph 4.2 further on addresses all the systems which are not lump system approaches. Let's look at the formulation of it, the mathematical formulation. The formulation is, we've got a solid body, and the solid body has a certain mass, a certain volume. Okay, so I'm using that V to distinguish it later on in the module where we use V for velocity. So that is why I use that V, and this is then for volume. Okay. Certain density, and the body is at a temperature Ti everywhere inside the body. So it's uniform and it's a lumped system. So all the temperatures on the inside is the same. It has a certain surface area, AS, and on the outside we've got the heat transfer coefficient and T infinite, which is the temperature of the environment. And in this case, I'm going to assume that the environment temperature is larger than the initial temperature, which means that the heat transfer will be from the outside to the inside. It can, of course, be the opposite. It doesn't matter. So the heat transfer rate going into this body can be written in terms of Fourier's law, which you've done with the previous module. It is equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature difference, which is T infinite, minus the temperature that varies as a function of time. And what we're going to do is we are going to take an energy balance by saying the heat transfer rate into the body during a period dt is going to be the same as the increase in energy of the body during dt. The heat transfer rate going into the body over a period dt is equal to the increase in energy dt. If you find it difficult in many cases to work with heat transfer rate, think of it as a mass flow rate. So the mass flow rate going into the tank would be equal to the increase in mass of the tank if nothing goes out. Okay. Let's write that in terms of the equations. It's the heat transfer coefficient multiplied by the surface area multiplied by Ts minus the temperature T over the time period dt is equal to the mass Cp dt. Now the mass, if we look at these two terms, that one and that one, the mass is equal to the density multiplied by the volume, and dt we can write as d of t minus t infinite. Okay. Why can we do that? Because this is a constant. And if we do the differentiation of the constant, it's going to disappear. If we substitute this into those two terms, then we can write the equation as the heat transfer coefficient multiplied by the surface area multiplied by Ts minus the temperature dt is equal to rho multiplied by the volume Cpd T minus T infinite. You happy with that? Okay, so what we're now going to do is we're going to get all the temperatures on one side of the equation and the rest on the other side. So we can write it as the heat transfer coefficient multiplied by the surface area divided by rho, the volume phi, Cp, dt is equal to d T minus T infinite divided by T infinite minus the temperature. Okay. Now it's almost in the form that we would like to have it so that we can integrate it. It almost looks like dx divided by x if we just change these two around. Okay, which means that we have to put a negative sign on that side, and then we can write it as d t minus t infinite divided by t minus t infinite is equal to minus the transfer coefficient multiplied by the surface rho v Cp dt. You happy with that? If we now do the integration, then we have to integrate that, and if we assume that all this is constant, we can say that when time is equal to 0, then this temperature is equal to Ti. Okay? And at time t, then that temperature is going to be the temperature at t. If you do the integration, you all know how to do it. It's just a simple ln term. Clean it up and make it neat. Then you're going to end up with the equation, the ln of the temperature minus T infinite divided by Ti minus T infinite is equal to minus the transfer coefficient multiplied by the surface area rho v Cp multiplied by T. We would like to get rid of the ln term, therefore we can say the temperature at any time t minus that of the environment divided by the initial temperature minus the temperature of the environment is equal to E to the minus Bt, where B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume Cp, and B doesn't have a physical meaning, but its units is per second. Thus, if we now look at the solution of temperature as a function of time, then we will always have the solution between Ti and T infinite. Okay. And let's suppose T infinite is now larger than Ti, then the solutions, let me just write the Ti there because it's going to be in the way, Ti. That is the solution for a specific value B1. So the temperature is going to do something like that. And as the time goes larger and larger, it will tend towards the temperature on the outside. Okay. If we make B larger, then it's going to do something like that and something like that. So it means that the solution as B increases, with quicker goes to T infinite. Okay, now, if we are now critical about it, we will say, well, that's now great. I've got this fancy equation that I can now use to solve the temperature inside the body as a function of time. But let's go back to this, and that is about the assumption of a lump system. When would I know I can use the lump system approach? When will it be valid or not? And that is one of the biggest challenges in this chapter for most students, figuring this out. Because in a test and an exam, I'm just going to give you a body, and you will have to choose which approach to follow. The lump system approach is most probably going to be 10 times or 100 times more simple than that of the other solutions. So it's quite a relief if you can use the lump system one, and it's much easier to solve. But it is not so easy to figure out when you can use it. And that is what I'm going to discuss with you now. So the criteria in terms of when is it a lump system approach, or when can we use a lump system approach? Well, before we answer that, one of the things that is being used is the characteristic length. The characteristic length. And the characteristic length is L, C for characteristic, is then equal to the volume divided by the surface area. Now this characteristic length definition is for lumped only. Of all the other bodies that we are going to do in this chapter, you have to be careful. In most other cases, you have to calculate or determine the characteristic length in a different way. So reserve this definition only for the lump system approach. We need to do that, and then we are going to get a number which is called the Biot number. The Biot number. And the Biot number, we are not going to derive it, but it's very easy to derive, and we are going to do it later on, is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. Now that's a mathematical definition, but what does it really mean? What it means is it is the convection, the ratio of the convection at the surface to the conduction within the body. The heat transfer convection at the surface the convection at the surface divided by the conduction within the body. And in terms of resistances, it is the internal resistance divided by the external resistance. So if we have a small Biot number, then we have a small internal resistance. Small internal resistance. So if the Biot number is equal to 0, then it is actually the lump system exactly. The problem is we do not have any real bodies in which the Biot number is 0. Okay, so that's a practical reality. So that is just a mathematical solution. All other bodies have a Biot number larger than 0. And now we have to determine when can we use the lump system, and we make use of the Biot number. And in general, what is being used as a good criteria is to say that is when the Biot number is smaller than 0.1. If the Biot number is smaller than 0.1, then typically we can use the lump system approach. And to get a small Biot number, if we look at this equation, then you will see it is typically when LC is small. When the characteristic length of the body is small, then it will make the Biot number small. The second thing which can be used to before the time figure out if you can use the lump system approach or not is to look at the thermal conductivity. If the thermal conductivity K is high, then normally we've got a very small Biot number. So if we just think of bodies that we can consider, then any small ball, a bearing typically, would have a small characteristic length, high thermal conductivity. So a ball bearing would be a good example of a lump system. The woman that wears some jewelry in your ear, that would typically also be a wire or maybe something fancy on, a heart or something like that. It is small, the thermal conductivity would be high. That would be a good approximation for a lump system. A dead body, okay, if there was a murder or somebody passed away and they have to determine when the murder took place, then they want to determine by measuring the temperature in the liver when the person was murdered. So a human being, in most cases, is not so small, and your thermal conductivity is relatively low, so that would be not a good example of a Biot number smaller than 0, or we can use a lump system approach. But what is more important is that you really understand this ratio of the internal resistance to the external resistance. It's all good and well to use the Biot number, but that is just to quantitatively have a criteria, but you will see in this module you need some deeper insight. And I'm going to explain it to you with the following example. This is the venue in which you are in the moment. Engineering 3, venue 1. Okay. And there are 300 of you in this venue approximately. And that is the door. And let's suppose We close 3 of the 4 doors, and there's a fire here in this venue. Okay, and remember, this represents the body, and the body I'm referring to is now this body. Okay, so what happens here on the surface is the convection heat transfer. So that represents you sitting here in the venue, and we've got this fire. And all of you want to move into this body. You want to go outside. Okay. Now, if there's one door and all 300 of you would like to get out of this venue as quickly as possible, there's going to be a big resistance. Why is the resistance? Because the resistance is being determined by the dimensions of that door. Okay. So it is going to be very difficult for all of you to get through that door very quickly. But if we open all 3 the other doors, the resistance will decrease, and you can move quicker outside into the other body. The resistance for you to move outside, to go to the outside, is much smaller. You understand? So it's very simple. Let's look at an example. The example is based on the one in your textbook. It's not exactly the same. I've changed it. And the example is about a thermocouple junction. The thermocouple junction has a diameter of 1 millimeter. Diameter of 1 millimeter. Okay. The K value of this junction is 35 watts per meter Kelvin. The density rho is equal to 8,500 kilograms per cubic meter. The Cp value is equal to 320 joules per kilogram Kelvin. The heat transfer coefficient is equal to 210 watts per square meter, either degree Celsius or degree Kelvin, it doesn't matter. And the initial temperature of this thermocouple is, let's suppose it's in the fridge or the freezer, and it's at 0 degrees Celsius. Okay, and it's 0 degrees Celsius everywhere inside this thermocouple junction. So at T equal to 0, if I can draw it larger, doesn't matter where you measure it, the temperature is going to be 0 everywhere. And also here on the surface, temperature is 0 degrees Celsius. Right, now at T equal to, when the time starts, we take this thermocouple junction and we put it in a stream or an environment where the temperature is now 100 degrees Celsius. Okay, so here it was in an environment where it was 0 degrees Celsius and we had steady state temperatures. So suddenly it is at 100 degrees, so it means that the temperature here on the surface everywhere is 100 degrees. Okay. Now the question is, how long before this thermocouple junction would be at 99 degrees Celsius? Okay, not 100 but 99. So it is within 1% of the 100 degrees. How long before it reaches 99 degrees Celsius? So if we do it schematically, we would say there's the temperature as a function of time. This is Ti, where it was originally at 0 degrees Celsius. T infinite is 100 degrees Celsius. Okay. At T equals 0, this body was at 0, and then the temperature is going to increase. After a very, very long time, it is going to be about 100 degrees Celsius, but we want to know that is 99 degrees Celsius. We want to know how long is it going to take before the temperature increases to 99 degrees Celsius. Right, the characteristic length is equal to the volume divided by the surface area. Now this thermocouple junction is a sphere, so the volume of a sphere is equal to 1/6 pi multiplied by d to the third divided by the surface area of a sphere, which is pi d squared. So the characteristic length is equal to the diameter divided by 6. The diameter is 0.001 divided by 6 meters. So that is the characteristic length of the thermocouple junction. Let's calculate the Biot number to see if the lump system approach is a good solution. It's equal to the heat transfer coefficient multiplied by the characteristic length divided by K. The heat transfer coefficient is 210. The characteristic length is 0.001 divided by 6. And the thermal conductivity is 35. So the Biot number is equal to 0.001, and that is smaller than 0.1, which means the lump system is okay. We can use it. Yep.
Sorry, you just assumed that the lump system was fine to work out the characteristic length. Should we always do that and then check the Biot number and then see if it's lump?
Yes, because in the Biot number you've got a characteristic length, and the question is then what length must you use? In this case it is quite a simple geometry, but it can be something which is very complicated. So for that reason it's a good approximation to say that the characteristic length is equal to the volume divided by the surface area. But remember what I said, this assumption you must only use for the lump system approach. In the other techniques that we are going to use to solve other types of bodies, then the characteristic length will be available in a table, or it would be part of the solution in terms of how you've calculated it. So for example, for a cylinder, a long cylinder, in this case you have the characteristic length that you must use is the radius. Okay. And if you're going to use the characteristic length for this, then it's not going to work. And if you make it 2 times longer, the characteristic length is going to change. But you'll see in the solution, it's actually a 2-dimensional solution, and you should actually just use another one, not this one. Okay. Right, so we can use the lump system approach, and we can calculate the value of B, which is equal to the heat transfer coefficient multiplied by the surface area divided by rho Cp in the volume. Take note that that is of course the characteristic length there. So this value of B can also be written as the heat transfer coefficient divided by rho Cp divided by the characteristic length. You see that? So that term there is equal to the characteristic length. You can calculate it in any way that you want. In any case, if we calculate it, then it is equal to 210, the heat transfer coefficient, divided by the density 8,500, CP 320, and the characteristic length 0.001 divided by 6, and that will give a value of 0.462 per second, because that is the units for B. Okay, now that we've got B, we can calculate the temperature as a function of time. Okay, with that equation that we've derived, okay, we would like to know how long it will take to get to a temperature 99 if the environment temperature, T infinite, changed to 100. The initial temperature is 0 minus 100. So you see the negative signs are going to disappear. It's equal to E to the minus 0.462 multiplied by T. T is the only unknown, and if we solve T, then it is 10 seconds. Very, very quickly, the temperature will increase to about 99% of where it should be. Okay, coming back again to what we said with the lump system. Remember, with a lump system, if I would identify certain points, 1 in there, 0.2 there, 0.3 there, 0.4 there, then it means that the solution of all of them, 1, 2, 3, 4, will follow the same path. Why? Because the resistance of getting out, of getting into the body, is very small. Okay. So if all of you are here on the inside, and there's only one door, and there's suddenly a fire, where normally one of you can get out of here jump out in 10 seconds, would get through the door. If it's all 300 of you, you can't get through the door. Okay, why? Because there's a resistance for you. But if we open up the other doors and even put in another 4 or 5 doors, then it's very quickly for all of you to move out and to move into the other volume. So the resistance for movement is very, very small. Remember, here on the outside, with conduction, we have molecules that vibrate, and that is how the heat is being transferred. They're at a higher temperature and they want to go to a lower temperature. It's the same with flow. If it's at a high pressure to a low pressure, always the same. It is the resistance that determines the flow rate, the mass flow rate, or the resistance for heat transfer that determines the heat transfer rate. Ladies and gentlemen, that was the lump system approach. Do you've got any questions? Nothing? Right, thank you very much. Then we'll continue on Thursday.